Alright friends, welcome back. So today we are going to be talking about fractions. Let me write that nice and big up here so we don't forget. Fractions. Sorry y'all, I'm still using a mouse. So not very good handwriting and it takes me a while to write things. Good combo, isn't it? So with fractions, there's some operations that we're going to be working with. We're going to be doing multiplying, dividing, adding, and subtracting. Um, and there's just going to be kind of a lot of concepts that we're going to be covering within that. So I do highly suggest that if you're watching this to better understand what we're doing with fractions, maybe take it in pieces, follow along in your paper as well, writing things down, especially with math, writing down, how to do problems over and over again. That repetition helps us to learn and memorize all of the steps involved. I'm also going to be doing my best to explain the why of why we're doing what we're doing, to kind of give you some reasoning, some mathematical reasoning for these processes, and hopefully that helps you out. But getting right into it, first I want to start with doing a little bit of a vocab review. So I'm just going to give a fraction here, 1/4, and our top number is called, hold on, aha, I'm so glad I remembered this. This is called the numerator, and then, wait, I should do an arrow here too first. I got too excited about typing. So that's our numerator, and this here is our denominator. Look at that, isn't that fun? So much better than me trying to write it out with my little mouse here. So numerator, denominator, and if you're really curious, this is called, it's wild, are you ready for it? This is called the fraction bar. Not that crazy, is it? At the end of the day. Okay. Sorry guys, it's gonna bother me. I want it close to the arrow. There we go. So we've got our numerator, our top number is the numerator, denominator, the bottom number is the denominator, and the fraction bar is what separates our numerator and denominator. So this specifically here is a proper fraction. And I'm going to give us a definition for that as well. A proper fraction is when the numerator is less than the denominator. So proper fraction when the numerator, in this case 1, is less than the denominator, in this case 4. So this is a proper fraction. So then we also have an improper fraction. So let's say I do 4 over 2. That was crazy. There we go. So my numerator, my top number is 4. My denominator, 2, is my bottom number. And this here, let me keep my notes consistent. There we go. Is an improper fraction. And that is the opposite of a proper fraction. So it's when the numerator is greater than the denominator. This is improper because fractions are supposed to represent a part of a whole number. So 1/4, that's representing 1/4 of one of something. So I can have, let's say, a pizza. Why not do a classic circle for fractions example? I have 4 slices. That is a crazy slice. There we go. That's a little bit better maybe. So I can have 1/4 of my pizza. And this is considered an improper fraction because I'm having 4 halves of something. So if I have a half of something, I only have 2 pieces, but I'm representing 4 pieces up here. So I'm actually representing 2 wholes like this split in half. And we consider that an improper fraction. So when we have an improper fraction, and we'll get into this later on, what we want to do is we want to convert it to a mixed number. So let's say I have 1 and 1/4. That is a mixed number. And a mixed number is just a whole number. So 1 would be my whole number, and a proper fraction, in this case 1/4, paired together. So here I've got 1 and 1/4. This is a mixed number. I've got a whole number paired with a fraction, a proper fraction. All right, so those are some definitions. I'm gonna put my mouse off to the side if you want to screenshot this or write down some notes or something. However, now I am going to delete it because I need this space so that I can show you guys some math. But it's good to get those words out of the way, that vocabulary, because I am going to be using these terms throughout this video. And delete. Oh, look at me go. I'm figuring it out, you guys. I might be a professional yet. Alright, so I did lie, there's actually going to be more words, but I needed space. So, we are going to start doing math with equivalent fractions. An equivalent fraction is when two fractions, oops, a capital H in my win there. There we go. And let's make this bigger. I don't know why it's doing this to me. When two fractions represent, I'm so sorry, y'all. Oh. Maybe I'm not a professional. Every time I'm like confident, I just do something to bungle it up. But anyways, when two fractions represent the same amount, but look different. So let's see an example of this. So let's go back to my 1/4 that I was using earlier. An equivalent fraction would be 2/8. So let's go back to my pizzas. I have a pizza with 4 slices. Let's say I only have 1 slice that I'm going to eat, or maybe 1 slice is left. Either way, something's happening with the 1 slice. And then my 2/8, so it's a pizza. Let's do a better circle than that. Okay, that was, I think, maybe worse actually. Alright, we're gonna live with this one. I'm not drawing any more circles. So this one we're going to split into 8 pieces. So there's, y'all, come on. I'm not an artist, okay? There's 4, 6, and 8 pieces. I fill in 2 of these. And this is not a perfect representation, but we can see that they are representing the same amount of space. And if you're real savvy with the numbers, you might even notice that all I've done is I've doubled my numerator, my top number, and my denominator, my bottom number, which is how I got my 2 and my 8. So all I did was I doubled 1/4. It's representing the same amount. Whoops. They just look different. There's different numbers. And there's different uses for why we might want to find an equivalent fraction. Say if we're simplifying, so we can take maybe 2/8 and divide it by 2 and get to 1/4. That would be simplifying. Or maybe we are adding two fractions with unlike denominators, unlike bottom numbers of the fraction. And then we'll get into it a bit more, but when we add fractions, they have to have the same denominator. So that's when we would make an equivalent fraction so that we can get them to have the same number on the bottom. So this right here, finding equivalent fractions, is super duper important for what we're going to be doing. All right, let's see. Getting into it a little bit more, let's just go ahead and let's multiply some fractions. So let me make another little header for this. I am loving the typing. Multiplying fractions. Can I make this bigger? I'm finding this out in real time, you guys. Whoa! Okay, that is exactly what I wanted. Let's give it a little underline for funsies. Look at that. I don't know if the sound effect was necessary, but it felt good to me. So, let's just get right into it. So you may have noticed it already when I was representing how we got our equivalent fraction of 2/8 over here. But multiplying fractions, I think I said multiplying fractions is really easy. Y'all, I don't know if I can talk. It's really easy because what we're going to do is we're going to multiply straight across the top and straight across the bottom. So I'll even write that out here as a little rule. I'll make that smaller again. Hold on. I want this to be different. There we go. Okay. Multiply straight across the top and straight across the bottom. That's our rule for multiplying fractions. So let's see it in action. Let's do something like 3/8 multiplied. Remember, I like to use my dot, but we could see multiplication as an X, as an asterisk, or even with parentheses. So we could have a fraction outside the parentheses and another fraction inside the parentheses. Or we can even see both of them in their own parentheses, like this. So different ways to do multiplication. I'll even include my dot just for the sake of having them all right here. I like to use the dot. It's a kind of algebraic way of doing it because when we have variables like x, it can be easy to confuse that with the multiplication symbol. And I'm a math major, so I'm doing a lot of math where I use my dot for multiplication, so a little bit of a force of habit for me. But whatever you use, really up to preference, all of them are correct. There's no wrong way to write it. Anyways, after that little brief interlude, let's do 3/8 and let's multiply it by 2/7. Why not? 3/8 times 2/7. So all I do is I multiply straight across the top my numerators. 3 times 2 gets me 6. And then I multiply straight across the bottom my denominators. 8 times 7 is 56. And just for the sake of not getting too confusing with anything, I'm just going to leave it straight as this. 6 over 56. 6/56. That's how you say fractions have names. So I like to use the fraction name. I understand saying a number over another number might be easier for you to understand. So I'll say it both ways, but the name of this fraction is 6/56. Notice how I'm putting that THS on the end, because this is representing a part of a whole. This isn't 1, it's less than 1, it's 6/56 of something. Kind of like when we talked about place values, how we have tenths, hundredths, thousandths. This is 6/56. Kind of fun to say, sometimes a little bit difficult to say even. But that's its fraction name. Let's see another example, just for the sake of doing it. Let's do 2/9 multiplied by 15/23. Why not? Just for funsies. Let's do some bigger numbers, get a little more practice. So here we have 2 times 15, which is 30. And then now we have, so that's multiplying straight across the top, and we multiply straight across the bottom, 9 times 23. Let's go ahead and set up a problem on the side over here. That's not supposed to be subtraction, that's supposed to be multiplication. I want to make sure that's very clear. So now I have 23 times 9. I multiply straight up to my ones place. 9 times 3 is 27. I put my 7 down below the 9 and the 3, and I carry my 2 from the tens place up to my 2 up here in the other tens place. Now I have 9 times 2, which is 18, plus 2, which is 20. I don't have anything else, so I don't carry over. I just plot my 20 right next to my 7. And now I know 23 times 9 is 207. So I'll go ahead and place that down here. And again, for the sake of keeping it simple and not bombarding you with a bunch of things all at once, we're just going to leave this as it is. That's the process for multiplying fractions. Multiply straight across the numerators and straight across the denominators. Multiply straight across the top, straight across the bottom. So yeah, that's pretty much just multiplying fractions. Now let's go ahead and get into dividing. I'll go ahead and do that right here. Let's boost this up a little bit. Oh, I love this whole typing thing. If I can type, actually. There we go. So now, okay, I had to make sure I was still recording. I was freaking out for a moment. So now we're going to be dividing fractions. So this process is a little bit different. We're actually going to use something called keep, switch, flip. You may have also seen this as keep, change, flip, they mean the same thing. If change is a better reminder for you than switch, absolutely. Use change instead of switch. Whatever it is, just keep it consistent. Until you feel comfortable with it, you could switch back and forth between keep switch flip and keep change flip if you like. But just, for the sake of not confusing you, I'm going to go with keep switch flip, and then I'll explain the keep change flip at the end. They do the exact same thing, though. It's just whatever works best for you, really. So I'm actually going to use the same example here, 3/8 and 2/7, but instead of multiplying, we're going to be dividing, because that's what we're doing now. So we're going to do 3/8 divided by 2/7. So keep, switch, flip. We're going to keep our first fraction, 3/8 will stay the same. I wish there was, yeah, okay, there is a way for me to change the color without also changing the size. I keep forgetting, I keep thinking these are the only 3 colors I have, but as you've noticed, the brush sizes are different, and that's not going to be super helpful for this one. So then we switch. We're going to switch our operator, or change our operator, if you will. We're going to switch our operator from division to multiplication, and then we are going to flip our second fraction. I forgot the word, my goodness. We're going to flip our second fraction. So 2/7 will flip to 7/2. This is also taking the reciprocal. So 7/2 is the reciprocal. It's the flipped version. Of 2/7. So we kept our first fraction, we switched from division to multiplication, and we flipped our second fraction. I'm going to re-say that because I think I just bungled that as well. We kept our first fraction, I think I said second. We kept our first fraction, we switched from division to multiplication, and we flipped our second fraction from 2/7 to 7/2. So now, all we've done is we've created a multiplication problem, which, as we saw from over here, we just have to multiply straight across the top and straight across the bottom. So 3 times 7, I get 21. 8 times 2, I get 16. And this is an improper fraction, but for now we're just going to leave it as is, just for the sake of not getting too confusing. This is just how you divide fractions. We change it to multiplication. And the reason why we're able to do this is because of the nature of fractions, as well as the relationship between multiplication and division. So fractions themselves are already division problems. 2/7 if we want to define the decimal of this fraction, we would do 2 divided by 7. 2 divided 2 divided by 7. And an interesting way to remember this is, let's look at our division symbol right here. Notice that it's a fraction bar with 2 dots. That could maybe represent anything. Fractions are just division happening. It's one number being divided by another number. So 2 divided by 7, if we wanted to do that, which I won't because that's a different lesson. You'll see that next week. That would get us our decimal that is equal to 2/7, our decimal for 2/7. So because I'm dividing division that's happening, I can actually flip my second fraction here and multiply it. I can do the opposite of what's happening here and get to the correct conclusion while making the math easier. So I hope that was easy to understand. It is a little bit hard to describe exactly what's happening here, but due to the relationship that fractions have of being division, and then the relationship that division and multiplication have of being opposite operators, they're Division is the opposite of multiplication. Multiplication is the opposite of division. I'm able to switch my division and take the reciprocal of my fraction here and make it into a multiplication problem. So let's go ahead and do another example, just for funsies. Let's go ahead and use our 2/9 times 15/23. We're just going to change it into a division problem. So I have 2/9. I think that 2 look a little bit better. 2/9 divided by 15/23. So I'm going to keep my first fraction of 2/9. I'm going to switch or change. Try to remember how I did this. There we go. My operator from division to multiplication. And then I'm going to flip my second fraction, 15/23, to be 23/15. And now we can just multiply. So I multiply straight across the top. 2 times 23 will be 46. And then straight across the bottom, let's go ahead and just set this up. 9 times 5 is 45. Carry over my 4 to the tens place. 9 times 1 is 9, plus 4 is 13. I don't have anything else to carry over, so I plot my 13 next to my 5. And now I know 15 times 9 is 135. So I can place that as the denominator for my answer. And again, we're just going to leave this as is. We're not going to do anything else. We're just looking at the process of dividing fractions using keep, switch, flip, keep, change, flip, whatever you prefer. All right. Let's see. Oh. Did you see how to pause for a moment and think? Okay. So now I need to clear off more space. But that is multiplying fractions and dividing fractions. So we're going to get a little bit more into just simplifying, reducing fractions, converting back and forth between a mixed number to an improper fraction to a mixed number, and then we will get into adding and subtracting fractions. So I am going to get rid of everything I have here, all my beautiful math work. I'm getting too excited with the lasso. There we go. All right, y'all. Just pretend that didn't even happen. I'm a professional YouTuber now. I'm going to delete fractions as well. Oh, I didn't delete it. Oh, okay. Everything worked out exactly how I wanted it to. I need to stop for a moment and drink some water, though. I'm a bit parched. All right. So let's get into simplifying, reducing, getting into lowest terms, simplest terms, smallest terms. There's a lot of different ways that you can hear it. So I'll put them all here. Simplifying, reducing, lowest terms. Simplest form is one that I say a lot myself. There we go. So these all refer to the same thing of just getting a fraction down to the smallest equivalent fraction that you can. So let's go ahead. I'm going to start with one that is fairly easy. It might be obvious to some of you, but just for example purposes, this is the one I'm going to use, and then we'll go into a more difficult one. So let's do 36/48. 36 over 48. 36/48 if you want to use its fraction name. So the idea is that there is some fraction that still represents the idea, the amount that 36/48 is representing, but it's just with smaller numbers, which scientifically human brains have a better time, an easier time comprehending and understanding smaller numbers than bigger numbers. So it's usually best practice to simplify, reduce, get into lowest terms, put into simplest form fractions so that we can better understand them. So there are two methods that we can use for doing this, and I'm going to show you the one that I prefer for students to do, and then I'm going to show you one that might be easier for students to do. So this first one is called, oh, hold on, let me type it instead of trying to write it all out with my mouse. So this first one is called prime factorization. Prime factorization. So here's what we are going to do. Whoops, there we go. We are going to find the prime factors of our numerator 36 and our denominator 48, and that is going to get us the greatest common factor. So let me also write that out, a little vocab over here. Greatest common factor. If you remember from school, you might remember this being referred to as the GCF. But essentially, what the greatest common factor is it's the greatest number that our numerator and denominator have in common that they can be divided by. So the largest, greatest, oh, okay, that's cool, number, oh, whoa, okay, that was an arrow. That was not at all what I was expecting, but that was fun nonetheless. Okay. I was gonna see if I couldn't get it to, oh, okay, look at that, y'all. I figured it out. Never mind. So it's the largest or greatest number that the numerator, I guess I'm going to make it more general, that any two can be divided by. So it's the largest, greatest number that any two numbers, in this case our numerator and denominator, can be divided by and still get a whole number. So let's take a look at this. I'm going to take 36, and I'm going to think of things that multiply to 36. And right off the top of my noggin, I thought 3 and 12. 3 times 12 gets 36. You could have done 9 times 4 even, or anything else that gets you to 36. I'm not going to list off all the ways you can multiply and get to 36, but I just need two whole numbers that multiply to 36. And the idea is that we're going to get to all of the prime numbers. So we already have one right here. 3 is a prime number. Oh, I guess I should also define what a prime number is too, shouldn't I? I'm getting ahead of myself, huh? A prime number. A prime number is a number that is only divisible, which means that it can only be divided and still get a whole number, by 1 and itself. So examples would be 1, 1's only divisible by 1 itself, which is still 1. 2, I can only divide 2 by 1 and 2 and still get a whole number. 3, I can divide 3 by 1 and 3 and still get a whole number. 4 is not prime because I can divide 4 by 1, 4, and 2. 5 is a prime number because I can only divide 5 by 1 and 5 and still get a whole number. 6 is not a prime number. I can divide 6 by 1, 3, 2, and 6. So definitely not prime. And then last one, 7 is a prime number. Not the last prime number, but the last example I will give. 7 is a prime number because I can only divide 7 by 1 and 7 and still get a whole number. So the idea of prime factorization is I'm going to get to only prime numbers. So now I have 12. And right off the top of my head, I know 2 and 6 multiply to get to 12. And I know 2, I can only multiply, or I can only divide 2 by 1 and 2 and still get a whole number. And then 6, I know 2 and 3 multiply to get 6. And look, I'm at my prime numbers. You don't have to write this out with the 1 and then the number itself to show it's a prime number if you already know. But I like to do it just to be extremely clear with what I am doing. So I'm going to leave it as that. I'm going to come back to this, but first I have to do my prime factorization of 48. So here I have 48, and I know right off the top of my noggin that 4 and 12 multiply to get to 48. I know 2 times 2 gets me 4. I know 2 is prime, so only 1 and 2 multiply to make 2. And then 12, again, just like over here, oops, I know 2 and 6. Just for the sake of doing something different, though, let's do 3 and 4. 3 and 4 multiplied together gets 12. So here, I have 1 and 3. Here, I've got 1, oh, 2, and 2. There we go. I almost did 1 and 4, and that wouldn't have been good. And those are prime, so I'm going to do my 1 and my 2 here. So now I've done my prime factorization of my numerator and my denominator. I'm going to find the prime numbers that they have in common. So I see a 3 here, and I see a 3 here, And I've got another 3 here, but I don't have any more 3's in my prime numbers here. So I'm not going to do anything. I'm not going to highlight this one. You can circle this if you want, just for the sake of having different colors and using a highlighter. So then I see I have a 2 here, and a 2 here, and I've got a 2 here, and a 2 there. So I have left over a 3, a 2, and a 2. There's nothing else I can match those up with, so I just leave them alone. But in common, there's 2 2's and a 3. So now, what I'm going to do is I'm going to multiply my 2's and my 3. 2 times 2 is 4, 4 times 3 is 12. So the greatest common factor for 36 and 48, and maybe you already knew this, is 12. This is my GCF. So now what I can do is let's come back over here. No, I'm actually going to keep it on this side because I don't have enough space for the second example either. So I'm going to keep it over here, and then I'll show you the second way we could do this on this side. So my greatest common factor is 12. What I'm going to do is I'm going to take my 36, 48, and I'm going to divide the top and the bottom by 12. I divide them, not multiply. I divide them by the same number. So to show it to you a little bit differently, and I want you to know very clearly that what I'm showing you is not 100% correct. Because if I take 36 48 and I divide by 12 over 12, 12 twelfths, I just showed you keep, switch, flip, right? So you're probably thinking, oh, keep this, switch this, get the reciprocal of 12 twelfths, which is just 12 twelfths, and multiply straight across the top, straight across the bottom. In this scenario, we're going to just divide straight across the top, straight across the bottom, and that is because I'm just dividing by 1. 12 fits into 12 one time. This is something that I like to call a special 1. This is a special 1. I'm not changing the value of 36/48, I'm just changing how it looks. And when I divide something by 1, I keep the value of it. So in this scenario, I'm just reducing, I'm simplifying, I'm getting my numbers into their simplest form, their lowest terms, by dividing by a special 1. So again, this is not how you divide fractions, but in this scenario for reducing, this is how you do it. I'm going to do 36 divided by 12, which is 3, and 48 divided by 12, which is 4. And so my final answer, my reduced simplest form answer is 3/4. All right, so that is prime factorization. I do prefer this method just because it's, how do I put it? It's kind of the most mathematical way to do it, and it's the easiest way, so that, or quote unquote easiest way, so that you are only dividing one time. There is a second method that I call plug and chug, and maybe you've heard this terminology before. Um, Teachers use it a lot to describe a lot of different methods, or a lot of different ways to use this method of just kind of brute forcing your way through something. This is plug and chug. And what I'm going to do is I'm going to take 36 48, and I'm just going to start dividing it by things until I get to my simplest form, until I can't divide anymore. And I do prefer this method less because you're just kind of, willy-nilly going through it, and you may stop too early. That is a common mistake I see with plug and chug. When you're brute forcing your way to get the right answer, you may stop before you actually get to that correct answer. But yeah, let's just go ahead and do this just for the sake of showing you, because it is another way of doing it, and as long as you do it correctly, you know to keep going and check your work. This will get you the correct answer, so it is a completely valid method. I just warn you, I implore you even to be careful. So 36, 48, they're both even numbers, and I know even numbers can be divided by 2, so let's just divide by 2 and see what happens. So I'm going to divide by my special 1 of 2 over 2, 2 halves, 2 seconds. 36 divided by 2 is going to be 18. 48 divided by 2 is going to be 24. And let's say I'm like, they're both even still. I'm just going to keep dividing by 2, seeing what happens. You could definitely divide by 6 or 3 at this point. But just for the sake of being like, maybe you don't feel as comfortable with your math facts, you're not quite sure how to go about it. You just know they're both even. I can divide by 2. Let's stick with that. So I divide by my special 1 again. 18 divided by 2 is 9. 24 divided by 2 is 12. Ooh, and now we're at an odd number. So some of you might think, oh, I can stop right there, that my numerator isn't even anymore, I can't keep dividing by 2. But we can definitely keep going still is the thing. So a good way to kind of check yourself is to skip count. So we know 9, not even, I can't skip count by 2. I can skip count by 3 though. So let's do that. 3, 6, look, there's my 9, 12. Oh, and there's my 12 too. So I can definitely divide both of these by a 3 over 3, 3/3, a special 1 of 3/3, to get another simplified answer. So I skip counted 1, 2, 3, 4 times. Divide by my 3/3, my special 1. Oh, that looks like a 7. My special 1 of 3 over 3. 9 divided by 3, that's going to get me 3. 12 divided by 3, that's going to get me 4. So we can see here I got to the same answer of 3/4 using a different method. This one is maybe not as beautiful as this method over here doing prime factorization, but in the end they both did still work. So I encourage you to try them both out. Try multiple problems using these methods, find what works best for you. I just implore you, be careful with plug and chug because you may stop too early. And it is a little bit difficult still to find, what number you can divide by, right? Like, what am I going to do? And, it's no longer even. I can't keep dividing by 2. I have to find something else now. Whereas the beauty of prime factorization is that I find all my prime numbers, and then I just find the ones that match between both my numerator and denominator. I multiply them together, and that's the only number I have to divide the top and bottom by so that I can get to my reduced answer. So that is simplifying fractions, reducing fractions, getting fractions into lowest terms, putting fractions into simplest form. Let's go ahead and talk about converting back and forth between mixed numbers and improper fractions. Oops. I'm getting there, y'all. All right, there we go. So let's see. Let's do converting to a mixed number from an improper fraction first. So let's make up an improper fraction. Remember, that's when my numerator, the top number, is larger than the denominator, the bottom number. So let's do 36/24. Why not? Let's keep working with numbers like this that are in 12s. So to convert to a mixed number from an improper fraction, the first thing that I want to ask myself is how many times does the denominator fit in the numerator? I'm dividing, my first step. Sorry, my lights shut off in my office because I'm just sitting at my desk. I had to activate them. My first step is I'm going to divide. How many times does 24 fit in 36? So let's find out. Let's do it off to the side over here. Oops. Let's do it like that. There we go. So remember, I'm dividing my top number by my bottom number. 36 divided by 24. So 24 definitely can't fit in 3, so we'll place a 0 over there. And just for the sake of showing you all of the steps, I'm going to go through this. If you already know that you don't have to do this, you feel free not to do it. I'm just showing it to be extra clear. So we just, if we go back to does McDonald's sell burgers raw, we just does divided. And now we're going to McDonald's multiply. 0 times 24 is just 0. Now we're going to subtract. 36 minus 0 is 36. We could burgers bring down another 0 if you want, just to kind of keep the steps concise. But we still have like a whole 36 to work with here. And now we raw repeat. So 24 into 36, let's skip count. 24 plus another 24 is going to get me 48, and that's already larger than 36. So we know 124 will fit inside of 36. So we'll put our 1 there, and we just divided. So now we're going to multiply. 1 times 24 is 24. We subtract. 36 minus 24 is 12. And we're going to stop there. We're not going to do anything else with our remainder here because we're actually going to use it. So we found out that there is one whole number. So if I rewrite this down here, 36 over 24, I know that there is one entire 24 24ths in here, plus, something else left over. Or 12 is what is left over, but we'll get back to that. Over 24. So we know as a part of our mixed number, we're going to have a whole number paired with a proper fraction. So we have our whole number part right here. We have an entire 1 from our 24 that we just took out of 36. And we had left over a 12. So what we're going to do is we take our remainder and we're going to place that over our denominator. So just to show you, 36 24ths is equal to 24 24ths plus 12 24ths. I can convert my 24 24ths into a whole number of 1. And then I just bring down my 12 24ths. Now we can simplify this though. So let's do that. So let's see, let me pull it all over here. So I had to think for a moment how I wanted to do this. We could plug and chug. I'm going to do prime factorization though, because like I said, I prefer that. So we're going to do 6 and 2. 2 is prime. 6, I can do 2 times 3. 2 and 3 are also prime. Now I have 24. I know I can do 2 and 12. Oh, and look, I'm going to do the exact same prime factorization for this 12 as I did for this 12 right here. I can literally write down the exact same thing. And looky there, I have a 2 here, a 2 here, a 3 here, a 3 here, a 2 here, and a 2 here. For 24, I had a 2 left over, but I'm not going to use it because I don't have another 2 with 12. I'm only going to use the numbers that match. So now I multiply. 2 times 2 times 3, which gets me 12. So my greatest common factor between 12 and 24 is just 12. So now I can divide my numerator and denominator by 12 each, or my special 1 of 12 twelfths. 12 divided by 12 gets me 1. 24 divided by 12 gets me 2. So my simplified answer is 1 and 1/2. And that's converting from a mixed number to an improper, or sorry. Y'all, I did the wrong thing. I did an improper fraction to a mixed number. That's embarrassing for me. So we just converted to a mixed number. Is that already what I had typed actually? I think I read it as converting a mixed number to an improper fraction, but we just converted to a mixed number from an improper fraction. I hope I didn't just make that all very confusing. I think I confused myself more than anything. But anyways, that's how we convert a mixed number to... I am just reading it wrong, I think is what I just realized. I'm more of a math person if you can't tell. That's like converting an improper fraction to a mixed number. There we go. I can speak, I promise. Alright, let's go ahead and do converting an improper fraction, sorry, a mixed number to an improper fraction. I'm going to convert a mixed number to an improper fraction. So just write that out, converting a mixed number to an improper fraction. And let me fix my typo over here. Converting the mixed number to an improper fraction. So let's go ahead and come up with a mixed number. Let's do 2 and 5/7. Why not? So there's actually a very nice little drawing I can do for this, and I suggest you use it if it helps you out. We're going to multiply our denominator by the whole number to get the fraction form of our whole number with the same denominator. And then we're going to add that fraction we just made to our fraction here, our proper fraction portion of our mixed number. So let's go ahead and show that. I'm going to multiply 2 by 7, which will get me 14. And I'm just going to place my 14 over my denominator here of 7. So I have 14 sevenths. 2 is equal to 14 sevenths. 7 goes into 14 twice. There's no remainder there. 2 is equal to 14 sevenths. That's it in fraction form with a denominator of 7. So now I can take my 2 in fraction form, my 14 sevenths, and I can add that to my 5 sevenths. And as you'll see with adding fractions here in a moment, we keep the denominator, so 7, and then do 14 plus 5, which is 19. And that is how we convert a mixed number to an improper fraction. It's the exact opposite. Notice how we had to divide when converting an improper fraction to a mixed number. This is the opposite. I'm going to multiply. All right. Let's go ahead and get into, let's see, how long has this been going? Oh, we're almost to an hour, y'all. I just yap so much, don't I? I think I'll actually leave this right here, and I will upload another video on adding and subtracting fractions in depth. I think I just need to take a little break for myself. But I hope that you learned something good from this, and if you need any... Ooh, sorry y'all, I've been talking so much. I'm not complaining, but I had a ton of meetings today, and then I had a tutoring session, so I've just been yapping. But if you need any more support, you can reach me at mbailey@pmi.edu. You can email me, you can come to my tutoring sessions. I could have typed down my email. I'm sorry, y'all, I was not thinking. But I also have tutoring sessions. And if you're watching this way in the future, because this is on YouTube, double check with me about these, maybe they change. But I will be on Tuesdays in the career prep classroom. Yeah, let's do it like this. In the career prep classroom, there we go, from 5 o'clock to 6 o'clock. On Wednesdays, I had to say it like that since I was typing, I will be in room 402 from 12:30 to 1:30. And then my final session of the week will be on Thursdays, back in the career prep classroom from 5 o'clock to 6 o'clock. And you are more than welcome to show up to any or all of these, or none of these, whatever you like, and I will support you however I can. So yeah, that's it, y'all. I hope you had a good time learning some fractions with me. I'll see you in the next one.